Welcome to the first afternoon session of CPP. I think it's on. Maybe I need to talk closer. All right. So this is the languages and compilers session, which I feel like is also every other session, but this is the one called languages and compilers. And our first talk is Katherine Kosaian. Did I get that wrong?
No, that's right.
And she's going to talk about a complete algorithm for real quantifier elimination in Isabelle.
Hi, yes, I'm Katherine, formerly Katherine Cordwell, and I will indeed tell you about our verification of a complete QE algorithm in Isabelle. So let's jump right in. Here are some examples of quantified formulas. So this one on the left is fairly simple. Here quantifiers are ranging over the real numbers. So on the left, this reads as, does there exist a real valued x such that x squared minus 1 is less than 0? This only has one variable, so we call it univariate. This example on the right is a lot more complicated. I have taken it from some of Pablo Pria's lecture notes. It involves multiple variables, so we call it multivariate. And these quantifiers, that there exist and for all, are difficult for both humans and computers to analyze. And the best way of handling them is to get rid of them entirely through a process known as quantifier elimination, or QE for short. So QE retains all of the logical meaning in a quantified statement, but it transforms our statement to a quantifier-free one, which is then much easier to work with. So on the left, QE will transform this problem to true, because this original statement is expressing a property of the real numbers. On the right, QE will transform to this. So here we have this free variable a, which was unquantified in our original problem. And so QE is identifying exactly what conditions on a are needed to make our original formula true. So this is an unintuitive example. I've chosen it to give you the sense that this can get quite complicated. So why do we care about these QE problems? So these real QE problems arise in a number of application domains. For example, geometry proofs, or stability analysis, which is important in chemistry and the life sciences. They also come up in the verification of cyber-physical systems. So for example, if we have a logical model of a Mars rover, we might want to answer some question like, for all starting positions of my rover, does there exist an acceleration so that I stay within a safe region? And also similarly, these QE problems arise in motion planning. So some of these examples are safety critical. If we're using quantifier elimination to answer some question in robot motion planning, we don't want the wrong answer. And this motivates the question, how do we do QE correctly? So a big result is that around 1930, Alfred Tarski proved that the theory of real closed fields is decidable. So algorithms to do this quantifier elimination exist. This is exciting. However, these algorithms tend to be fairly mathematically intricate, and that makes implementing them correctly difficult. So our approach is to formally verify these algorithms in theorem provers, and thus get correctness guarantees. So for us, we start with a QE algorithm. We translate it into the theorem prover that we use, which is Isabelle. We prove correctness properties, and at the end of the day, we export our verified implementation of the algorithm to SML code. There's a couple of things that I want to highlight about this pipeline. So translate is maybe a misleading word. These algorithms are mathematical, they're complicated, they are sometimes initially quite sketchy, and so we really have to take whatever we're given at the start of the day and put it into the most rigorous setting. So this is quite the burden, actually. This is a major step. The other thing I just want to point out is that we use Isabelle's code generator for this code export. So this hasn't been fully formally verified, so at the end of the day, take our code export with a little bit of a grain of salt. There's work in progress on that. Okay, so to my knowledge, here's what the state of complete QE algorithms in theorem provers looks like. And by complete QE algorithms, I mean a QE algorithm that's capable of solving any quantifier elimination problem. So there are two implementations that I know of. The first is a proof-producing implementation of based on the Cohen-Hormender algorithm. This was done by Sean McLaughlin and John Harrison in HOL Light. By proof-producing, I mean that it takes a QE problem, produces an answer, and a proof that that answer is correct. So this loses some efficiency compared to just verifying the Cohen-Hormender algorithm. There's also a verified version of Tarski's original Kiwi algorithm in Koch by Asia Mahboubi and Cyril Cohen. So one thing that you're seeing in this table is that there's little red X's in the complexity columns for both these underlying algorithms. And that's because both Cohen-Hormander and Tarski have non-elementary complexity, so their complexity is not bounded by any tower of powers of 2, which makes them impractical for real-world use. The best known quantifier elimination algorithm is cylindrical algebraic decomposition, or CAD. Unfortunately, only the univariate case of CAD has been verified. This has been done independently in at least 2 different theorem provers, but the multivariate case has been a major challenge. So why might this be? So one thing is that the multivariate case of CAD is significantly more complicated than the univariate case. In contrast to, say, Cohen-Hormander or Tarski, where the multivariate case builds somewhat directly on the univariate case. So what you see in this table is a little bit of a trade-off between the computational complexity of an algorithm and its amenability to verification. In our prior work, my collaborators and I identified a potential sweet spot in this table. So we're interested in an algorithm based on the Benor, Kozen, and Reif paper, which described a decision procedure. So this was later extended into full Kiwi algorithms by multiple people who ended up getting very good, compelling parallel complexity bounds on their algorithms. So that's why we're kind of interested in the complexity of these algorithms. And also, these algorithms seem like they may be amenable to verification. So in our prior work, we verified the univariate case of some of these algorithms. And in our current work, we extend that univariate verification into a multivariate result. So we don't fully achieve all of the efficiency insights from the original BKR paper. We do trade off a little bit of complexity for ease of verification. I'll be telling you more about our design decisions as the talk progresses. So hopefully this will make more sense soon. But we do achieve this multivariate algorithm. All right. So now that I've told you a little bit about where my work fits in context, let me tell you about the actual algorithm that we formalize. So the Benor, Kozen, and Reif algorithm and Tarski's Kiwi algorithm both transform the Kiwi problem into a sign determination problem. So we're going to look at a set of polynomials, and we're going to try to find their consistent sign assignments. So a sign assignment is a mapping of polynomials to the 3 possible signs, positive, negative, 0, and it's called consistent if it's actually realized at some real value. So why do we care about this? So let's say we start with some Kiwi problem. Does there exist some z such that p of z is greater than or equal to 0 and q of z is less than 0? So z could be a vector. It doesn't have to be a single variable. It could be multiple variables. Well, if we know all of the consistent sign assignments for p and q, then we can just check. Do we have one that's positive negative or 0 negative? Because those are the only 2 sign assignments that would satisfy this original Kiwi problem. So that's how we decide whether this original Kiwi problem is true or not. This is a simplified example because, it reduces to true or false. But this is the intuition for why we care about sign determination. Okay, another key idea in both the Benor, Kozen, and Reif paper and Tarski's original algorithm is to treat multivariate polynomials as univariate in some variable of interest. So I'll always call our variable of interest x. And this is called projection. And the reason this projection is efficacious is because in the univariate cases of these algorithms, the only information we really need computationally is the signs of the polynomial coefficients. So if we never need to know the values of our coefficients, well, in our world where the coefficients are now polynomials, we can still make progress. So for example, if we have this Kiwi problem shown on the slide, so our variable of interest is x. Let's treat our coefficients as just something that we want to obtain sign information for. And then we can apply univariate techniques to solve this overall Kiwi problem. This is like the basic idea. In case this is sounding a little simple, I do want to point out that using multivariate polynomials in a very logical setting is not actually simple. So even just treating a multivariate polynomial as univariate requires a type change. So in Isabelle, we go from the type of real multivariate polynomials to the type of univariate polynomials with coefficients that are real multivariate polynomials. So even simple things become a little more complicated. That aside, what we really need to know is how to do sign determination on these coefficients. And here, the BKR algorithm and Tarski are going to differ. So what BKR is going to do is it's going to do a recursive call. It's going to use like a sledgehammer call to the overall sign determination algorithm to solve for sign information for these coefficients pictured in green. Tarski's algorithm, on the other hand, is going to naively or just branch on all the potential sign assignments. So we're including some branches that we don't strictly need to, but we're also limiting the recursion of our algorithm. So one thing about a super highly recursive algorithm is that it's difficult to formalize. Because in a formalization, you want to be able to modularize your proofs. You want to be able to take a big proof and break it apart into little chunks. And so working with the BKR algorithm is a bit challenging because it's super, super highly recursive, whereas if we go for a little bit more of the Tarski style, we limit the recursion of our algorithm. And that's why we currently make the design decision to go for Tarski style when we do branching. Okay, let me show you a bit of an example. Let's say we start with this QE problem that I'm showing you on the slide. The first thing we're going to do is we're going to focus on the innermost quantifier. So now we have this QE problem in orange. Now we're going to pick out our polynomials of interest, and you can see we're going to solve the sign determination problem for these two polynomials, where these green coefficients we're going to need to branch on. So in this example, it's just y squared because I've chosen it to be simple. Our first branch is going to say, what happens if y squared is greater than 0? All right, here are your consistent sign assignments. Next up, what if y squared is equal to 0? Same thing, here are your consistent sign assignments. And finally, what if y squared is less than 0? Here are your consistent sign assignments. And you'll notice this last branch is not consistent. We never have y squared less than 0. But our algorithm doesn't yet realize this, so it's still going to include this branch. All right, so next up, we're going to look for which of these sign assignments actually satisfy this original problem. So I've pictured those in green. And in order for us to care about a branch, we need all of these sign assignments in a branch to be green, because we have a universal quantifier here. So that means that our first and third branches are useful for us, but our second branch we're going to not include anymore. So at the end of the day, we're going to get this output where we include a disjunction of the two useful branches, and we include this existential quantifier from our original problem. One thing that you might notice, we've included an inconsistent branch in our output. This does not matter logically, because when we go to eliminate the quantifier on y, this branch will get pruned out. So you know it's not great for efficiency that we have it around, but it doesn't affect the logical correctness of our algorithm. All right, so that's like kind of the first step. Now I need to dig a little bit more into sign determination. So sign determination is a very continuous problem, and we need to be able to make progress on it in a computer. How do we do that? So actually, we're first going to transform our problem. Instead of just looking for the consistent sign assignments to some set of polynomials, we're going to look for the consistent sign assignments at the roots of some auxiliary polynomial. All right, so I'm mostly blackboxing this step. The intuition is that this is a more computable format of our problem. In the univariate case, this is a completely discrete problem. In the multivariate case, it's not exactly discrete, but if you think about projection, you can kind of see why this helps us make progress. And now let's dig in a little bit into how the univariate algorithm would solve this discretized sign determination. So it will do this with a matrix equation. So this is how Tarski's algorithm would work. Tarski's algorithm is going to go through all potential sign assignments, and it's going to construct a matrix equation to solve for this left-hand side vector. So this first entry, for example, of the left-hand side vector, is storing the number of roots of p where the qi's are all positive. The second entry is looking at the number of roots of p where the first n-1 qi's are positive and the last one is 0. And it goes through all of the 3 to the n possible sign conditions. And so Tarski's algorithm is actually explicitly going to construct this matrix M for us. It's going to compute this right-hand side vector with what's known as a Tarski query. I'll tell you about how those are computed in just a few slides. But I'm blackboxing the correctness of this matrix equation. It relies on an underlying mathematical result known as the Sturm-Tarski theorem, and the details are very beautiful and in the paper. The reason I show this to you is that BKR also constructs a matrix equation, but a smaller one. So BKR is going to inductively do a construction where it starts by forming a matrix equation for a single polynomial q, and then in a divide and conquer sort of style, smaller systems are successively combined, and after each combination, there is a reduction. So we get rid of inconsistent sign assignments. And at the end of the day, this leaves us with a matrix equation of size O of degree p instead of 3 to the n. So we like this reduction. So this was univariate, and what's really exciting is that in all these things I just showed you, a matrix is agnostic to what data it's storing. So a matrix doesn't care if it has data in it for univariate polynomials or for multivariate polynomials. And this means that when we go to do a generalization from our univariate formalization, well, if we have some matrix operations that are doing reduction, we basically just inherit that for free. So this is wonderful. There is one big piece that has to be generalized to go from univariate to multivariate, and this is the computation of the Tarski queries. So how, on a high level, are univariate Tarski queries being computed? Well, this is very high level, but essentially, we form a Euclidean remainder sequence. We pick out the leading coefficients from that, and we form two new sequences. Then we take the number of sign changes in each of those sequences, and we return a quantity calculated from the number of those sign changes. Again, very high level. But the takeaway, in this computational pipeline, we only care about the signs of the coefficients. We never query on the value of a coefficient. And so this means that when our coefficients are multivariate polynomials, we can still do a computation just like this. So our hybrid algorithm is going to branch naively on the signs of the coefficients to do this computation. In the BKR algorithm, you would do a recursive call and you'd get more efficiency. But this is kind of how the multivariate generalization is working. And I want to point out, this is actually a really big challenge point in the formalization. So generalizing these Tarski queries was hard. We benefit from some existing formalizations in Isabelle by Wenda Lee, but there are some mathematical details here that I haven't quite shown you, like we can't just really use a Euclidean remainder sequence that would give us fractions. We don't like fractions. Instead, we're going to use a mathematical tool called pseudo-remainder sequences. So there are some details that are in the paper if you're curious. We also use some fancy tricks like custom induction theorems in Isabelle to make our formalization go through. Takeaway, this was a challenge point. But once we sort of surpass this hurdle, then we naturally inherit some nice things from our univariate case, like this matrix reduction, because again, matrices are agnostic to what data they store. And I just want to give you a sense of why we like this reduction. So in our univariate paper, we considered some micro benchmarks, and we compared the number of Tarski queries that we would need to do in an unverified version of Tarski's algorithm versus our verification of the BKR algorithm. And you can see there are really drastically different numbers in this table. And this matters because these Tarski query computations appear to pose a bit of a computational bottleneck in the univariate case. So we like our reduction. Okay, I just want to give you just a few more details about our formalization so you can get more of a flavor of what we did. First of all, it's 8,500 lines of code. It's publicly available on the Archive of Formal Proofs. We do share some theoretical overlap with the prior work by Cohen and Mabubi, who formalized Tarski's QE algorithm in Coq, and then also some unpublished work by Cohen, who looked at building reduction just into the matrix equation. But again, the formalization flavor of our work is very different from the formalization flavor of this prior work, because we started with a case where we had reduction in the univariate case, and we built into a multivariate algorithm where we again have reduction, and they're just very different flavors. I mean, also theorem proving in Coq is different from theorem proving in Isabelle. I'm happy to talk more about this. All right, so multivariate polynomials. I already alluded to the fact that working with multivariate polynomials in a theorem prover is hard. So we benefit from some prior work that we had done on verifying an efficient incomplete QE algorithm known as virtual substitution, which is not capable of solving any QE problem, but it works on a fragment of QE problems, and when it works, it's quite efficient. So we inherit nice libraries from this prior work, and we also build it as a pre-processing step on our verification, so we can retain the efficiency benefits that we had formalized already. Despite having pretty good libraries to start with, there are some results that are just missing. So we end up needing to add results for any polynomials, if they evaluate to the same number on any input, then they are identically the same polynomial. So this is a fundamental mathematical result that we couldn't find in the libraries, and it took us some time to formalize that. All right, The other thing I want to point out is that this work involves a lot of non-trivial design decisions. So a lot of things that are now obvious in retrospect were not obvious when we were starting out. So first of all, whenever we branch, we need to track the assumptions that we're making. It sounds really obvious when I'm telling it to you now, but you can formalize a matrix equation with reduction that doesn't actually track the assumptions, and it's fine, except when you go to turn it into a complete QE algorithm, and then you experience pain, and you change how you do your algorithm. So in retrospect, there are some things that are obvious that we didn't know initially, because our algorithm that we started out with was very mathematical, pretty underspecified, and we had to make it very logical. Also, we hadn't perfectly set up our univariate case for generalization. So this isn't entirely surprising, because multivariate polynomials are much more complicated than univariate polynomials and pretty fundamentally different on a number of levels. But there was definitely a place in our univariate case where we had to go back and massage what we did to change it so that it would generalize. All right, so in conclusion, we have formalized Isabelle HOL's first multivariate quantifier elimination algorithm. It is a mixture of BKR and Tarski. We target this potential sweet spot between computational complexity and ease of verification. In the future, we'd like to add in the full reduction of BKR. We'd also like to aggressively optimize our formalization. And in the far future, we're interested in looking at variants of BKR that have very compelling parallel complexity bounds. So thank you for your time. Are there any questions?
Any questions?
Oh, that was me. Thank you.
Thank you for the talk. Just curious, is the BKR complexity elementary?
Okay. Let me tell you about the complexity results. So in the original BKR paper, there was an error in the complexity analysis, which was later fixed by some researchers like Renegar and Canny and others. And it also depends on what metric you're looking at. So I will not try to say what the complexity of the original BKR algorithm was, because I don't know if anyone has definitively given the correction. Future work that fixed it didn't exactly say necessarily what it was, but they fixed it. And so Renegar, the parallel complexity bounds, I believe, are even better than the parallel complexity bounds for CAD, or cylindrical algebraic decomposition. That being said, take a complexity bound with a little bit of a grain of salt, because it doesn't always immediately translate into efficiency. So CAD is still the workhorse algorithm of QE.
Thank you.
I actually didn't catch that. Is it elementary or not?
I don't know, because there was an error.
Okay.
So they claimed a very strong result, which was later fixed. But I will not speculate on the actual complexity of BKR.
Well, related, but just on the more practical side, did you try? So you have a mix of BKR and Tarski. Did you try it on examples, and how does it perform compared to BKR to CAD?
So currently, our multivariate algorithm is not efficient, unless we have virtual substitution doing the efficiency for us. But currently, we just don't have efficiency. We also haven't really optimized. So the BKR algorithm is super parallel. Isabelle's libraries for parallelism are a little bit preliminary at the moment. So we haven't built our formalization to be parallel. So there's a lot of places where we're losing efficiency. We're also losing efficiency because we're mixing it with Tarski's algorithm. So right now, I am not claiming that we are efficient. We are very not efficient. But we are hopefully on the path towards better efficiency.
Let's thank our speaker again.